Hello, welcome to 13 Universal, Learning Beyond Barriers, and this is A-level CIE biology session with schedule. So when you call me schedule, we roll. Okay, guys. We're going to be solving questions on CIE biology. I want to also mention that the questions came from CIE past questions. All right. So this is biological molecules. Series 2. Okay, we've done series 1. Watch it and give us your feedback. So this question, the first question here goes, the diagram shows part of a molecule of glycogen. So that's glycogen. Glycogen is highly branched, it has many free ends. Okay, that gives it compact structure. You can see, glycogen highly branched. You can see that. Okay, and so watch this. So how does the molecule differ from a molecule of amylose? Okay, so let's look at it. Okay, so now both of them are made up of alpha glucose. So if you look at options, look at the first option. Amylose has only alpha one. Okay, this is alpha, this is alpha. Look for alpha. So the ones that have beta, remove them. Okay, because it's only cellulose that they're made up of beta glucose. So alpha. So our options are narrowed to A and C. So let's look at A. Amylose has only 1,4 glycosidic. This is correct. So 1,4 is for straight chain, while 1,6 is branch chain. So amylose has only 1,4. It doesn't have 1,6. Okay. Amylose doesn't have 1,6. It's not branched. It's unbranched. But glycogen has 1,6 and 1,4. In fact, it has more 1,6 because it's highly branched. Because of that, the answer is A. All right. Okay. So let's go to the next question. It says, which molecule contains a carboxyl group? So I'd like you to pause your video and try this question. Okay, number one is amino acid. Does it have a carboxyl group? Glycerol, does it have? Saturated fatty acid, does it have? Unsaturated. So which one? Pause it. All right, so we have all the options here. All right, which one do you think has carboxyl group? Okay, so but you see, guys, if you remember the structure of amino acid, this is the structure of amino acid. This is, of course, this is carboxyl group. So amino acid has carboxyl group, right? Yeah, that's carboxyl group. So it has carboxyl group at one end, and of course it has amine group, which is NH. Okay. Now, sorry for the slow writing, but watch this. So it has carboxyl group. That's all we needed, right? So the entire structure of amino acid, of course, if you put R here, that is the R group, and H here. This is an amino acid, okay? So what differentiates them is just the R group. So, but the point is that amino acid has carboxyl group. That's it. So this is carboxyl group, COOH. Okay. Now, so this is it. This is part of it. So let's come to glycerol. If you remember, glycerol has 3 carbon compound. If you remember the structure of glycerol, does it have carboxyl group? Glycerol has more of hydroxy group. Okay, it has about 3 hydroxy group attached to each carbon atom, right? So it does not have carboxyl group, right? So it has only OH. Okay. Now the other parts are surrounded by hydrogen. So hydrogen is here, hydrogen is there, hydrogen is here, hydrogen is here, hydrogen is here. So more of the functional group is OH here. So it doesn't have a carboxyl group. Now if you come to fatty acid, now saturated fatty acid is saturated. Now they have fatty acid. There's fatty acid here. So they have carboxyl group. Fatty acid have carboxyl group. Unsaturated fatty acid has fatty acid. So also have carboxyl group. So both amino acid, saturated fatty acid, and so they all have carboxyl group except glycerol. Glycerol doesn't have it. All right, so is 1, 3, and 4. Yeah, you're right. Okay, guys, don't forget to like our videos. Okay, share, make comment. All right, and of course subscribe. So go to next question here. It says the diameter of some atoms when they form, okay, bonds are given in the table. So the bonds of these atoms have diameter, okay? Yeah, they have diameter just like circles. Okay, that's it. So, all right. So every atom has a diameter because as a spherical shape as from the center across the circumference. So it says the length of the amino acid shown below was estimated using these figures in the table. Okay, look at it. All right. This is an amino acid. So from here to here, the length, that's 0.7 nanometer. So the question says, what would be the approximate length of a dipeptide formed using this amino acid? Okay, that's it, guys. Pause the video and check it. All right, and then work on it. Let's see what you get. But if you check, guys, see how did they get 0.7 nanometer? How did I get it? Okay, so now see how they got it. I want you to pick up your calculator. Now start adding hydrogen here, single bond 0.060, okay, plus, so 0.060 plus nitrogen, which is 0.140, plus carbon, which is 0.154, plus carbon again, which is 0.154. Are you adding? Then plus oxygen's single bond, of course, um, which is 0.132, and then hydrogen again. Okay, so by the time you are done, you must get 0.73, and that's how they got this. So if we have this twice, all right, remember that during condensation, all right, so one amino acid, this is amino acid, the one we have there, plus another amino acid, all right. So if you add up these two amino acids, which are the same length, we're going to have a dipeptide. A dipeptide consists of two amino acids linked by hydrogen bond, peptide bond, right? That's a dipeptide. But of course, water is produced. So water is always formed because this is a condensation reaction, which always produces water molecule. So what we're going to do here, guys, is that remember that the length of one amino acid is 0.7. Okay, yep, this is 0.7. Yeah, plus 0.7. Okay, so that should give you 1.4. Okay, but you see we're removing hydrogen, two hydrogen atoms and one oxygen atom in form of water. Okay, so we're removing water. So what will be there is that we're going to find the length of water. See, water is like this. This is water molecule. This is hydrogen attached to oxygen using a covalent bond. Okay, so the length of water molecules, we're going to just find that and then minus it from 1.4. How did we get 1.4? By adding this amino acid. So you add this. So what we're going to do is that you add this and this. One length is 0.7. That's what they showed us here. Plus another one 0.7. And then we have this dipeptide, but minus water. This water came from this amino acid, all right? So add it and minus water. All right, let's find what water represents and then take it away from 1.4, okay? All right, so now let's go to work, guys. Get your calculator, let's do it. All right, so now remember that hydrogen single bond, this, that's what we have here. Water pair, oxygen pairs with hydrogen with single bond, and that is 0.060. So that's 6. plus oxygen. Oxygen single bond, that's it here. 0.132, guys. Are you with me? Punch it. So 0.06 plus 0.132 quickly, plus this hydrogen again. So add hydrogen again, single bond, diameter, which is 0. All right, 0.60 whatever. Okay, by the time you add it up, that will give you what? Add up everything. What do we have? Add up 0.06 for this hydrogen, single bond, 0.132 for this oxygen here, and then this 0.06 for this oxygen here. Punch your calculator. Tell me what you got. Okay, so you must have gotten 0, all right, point 252. Check it out. 0.252 when you add up everything, okay, for water, and then you now minus it from 1.4. So 1.4 minus 0.252. Okay, yeah. So what did you get? So you're gonna get something. I think I'm gonna get 1.146 thereabout. Okay, 1.146. So this is the answer. So we'll go to the option. Which one is closest to it? 0.9 is not close to it. 1.4 is far away. 1.7 is far away. So the closest answer is 1.2. All right. That's 1.2 nano. This is nanometer, not millimeter. There's a typographical error. Okay. 1.2 nanometer. That is the answer. Okay. So want your feedback. So what do you say about the question? Want to hear from you. Okay. Let's go to the next question. Yeah. Which feature of water is least now? The one that is least. Every one of them. See, this is least. Please, it's emboldened. That is a signal to you. Least likely. That means every one of them have effect, or least likely to affect the life of an animal in a tropical rainforest. Tropical rainforest have a lot of trees. Rainforest is high, a lot of high-rising trees, canopies, tall trees. So we're looking at the property of water that helps this animal. Remember, it's an animal. Okay. So which one? This is an animal. Okay. Now, adhesion with other molecules. This adhesion is what makes water, right, a solvent. So that's why water is a universal solvent. Okay. And of course, that helps to transport materials inside this organism and across it. Especially if this organism is multicellular. Adhesion helps water to transport molecules. For example, if an animal, blood would dissolve, blood plasma dissolves, all right, gases, nutrients, glucose, amino acid, the rest of them, and other waste material and proteins. So it needs this to transport material inside of it. This with inside. Of course, we're dealing with the animal. Now, plants also need to transport water, and the animal depends on the plant, but most especially inside the animal, this is needed for transport. All right, very important. Cohesion between water molecules. Okay. Yes, that is needed also for water to have the property. Remember that because of cohesion, water molecules form hydrogen bonds within each other, and this is why water molecules have high heat capacity. Okay, so high heat capacity is due to cohesion. All right. Okay, this is due to cohesion. Okay, that means that high heat capacity, specific heat capacity, means that water responds slowly to change in temperature. So water helps to maintain the temperature of this animal, constant temperature. This is very important for this animal to survive. Okay. Now, high latent heat of vaporization also, water requires a lot of heat to change from liquid to vapor, and that removes excessive heat from the body of this animal, and it prevents enzyme denaturation. This is important for its survival. Now, when we go to low viscosity, water has low viscosity. It's very important because it allows water to, all right, allow blood circulation. Because of low viscosity, blood can circulate, or any other fluid that's responsible for transport, any other transport medium will need low viscosity. Because of water is a major component of transport medium, especially blood. Okay, now this is inside this organism. Now, maximum density of water at 40 degrees Celsius. This is important because at this density, of course, you know that this is the maximum density. All right, so if water has this, all right, that means that at temperature below this, ice is formed, and ice can float on water, and the ice can insulate water, other aquatic lives, all right, from, so they insulate aquatic bodies from freezing completely. If you remember, guys, okay, if you remember, watch. So you see, this actually um, is a list. This is a list. Why? This has to do with environment where the organism lives. Alright, this has to do with inside of the organism. This has to do with inside of this animal. Inside. So all of them are very important. This has to do with the environment. Okay. So it prevents the freezing, alright, of water bodies at winter. But this is only important if the animal is aquatic. If this animal is not aquatic, it doesn't need this. All right. So this is the least important. All right. Okay. So let's go to the next question. So two solutions, one and two, one containing starch and sucrose, and other containing glucose and protein. So one of them contains starch and sucrose. So anyone that has starch will have sucrose. The one that has glucose will also have protein. Is that okay? It's very important to understand the question. It said they were tested with variety of reagents to confirm the identity. Okay, let's see what happens. So the table shows conclusions from the results recorded. So this is conclusion. Remember, the one that tests positive. Now this is test for starch. That's test for glucose. That's test for sucrose. Okay, that's test for protein. So the one that has starch will have sucrose. So let's check the one that has test positive for starch. Okay, option A, this one tests positive, and option C positive. Let's check whether this one tests positive for sucrose. No, it doesn't. This is test for sucrose. It doesn't. Okay, that eliminates option A. Of course, B is wrong, D is wrong. All right, if you check C, this solution one tests positive for starch. It should test positive for sucrose. That's what it means there. Okay, that's correct. All right, and if the other one tests for glucose, positive for glucose, so we use binary solution to test for glucose. It should also test positive for protein. So the same C, two tests positive for glucose and also test positive for protein by adding burette. Burette is used to test for protein. So what do you think is the answer? It is C, of course. All right, let's go to the next question quickly. It says the structural formula of a carbohydrate molecule can be shown as this. All right, I think we've done this question before. There's a which of the molecules could be represented by this formula. This question is repeated a lot. Oh, okay. The answer appears before the other options. All right. This question is repeated a lot. Okay. So the question is, why is it a SSB beta glucose? Why? Because glucose is hexose sugar. Or it has 1, 2, 3, 4, 5, 6. 6 carbon sugar is hexose. Deoxyribose is 5 carbon. Ribose is 5 carbon. So none of them is 6 carbon sugar. So the answer is A, because glucose is hexose, 6 carbon sugar. Alright, number 7. The diagram shows part of a molecule of a carbohydrate formed by glucose. So this, we have done this question at the beginning. Okay, so let me ask you, what molecule is this? Tell me again. Tell me again. Yeah, you were right. I heard you. Glycogen. So that's glycogen. So what is the name of the molecule? That's glycogen. It's highly branched, highly branched, highly branched. More 1,6. So let's check. Amylose, nope. Amylose is not branched. Cellulose is not branched. Okay. Yeah. Yeah, of course. Starch has amylose and amylopectin, but none of them, of course, amylose is not branched. Amylopectin, it doesn't have this branching, right? So it's glycogen. You're right. You're right. Let's go to number 8. So a naturally occurring polysaccharide is a branched chain. Now, it's made up of, it's a chain branched. Please pay attention to these key features. Number 1 is branched, and then it consists of alpha glucose. This is alpha, not A. Alpha glucose. So the straight parts of the molecule are linked by 1,6 glycosidic bond with a small number of branches. Okay. Yeah, this has small, it's branch, but it has small number. So I wanted to guess which polysaccharides, okay, is branched but has few branches. Okay. Then they say which are linked by either 1,3 glycosidic bond or 1,4. So which polysaccharide would that be? That's what they're asking. So which polysaccharide has a structure most similar to that described? That means it is branched. All right. The monomer is alpha glucose, but it has few branches. Pause the video and figure it out. Let's check. Which one? Amylopectin. Is that correct? Amylopectin is made up of alpha glucose. This is alpha glucose. This is alpha. This is beta. This is eliminated. This is highly branched. This is not branched. This and this are branched, but this is highly branched. But this one has few branches. So amylopectin, of course, is the answer. All right. So look at this. Which molecule has properties that are not dependent on hydrogen bonds? Not dependent. Not dependent. So you don't need hydrogen bond. Okay, look at the cellulose. Yeah, cellulose, glycogen, hemoglobin. So which of them is not dependent? Now cellulose is dependent on hydrogen bond because cellulose molecules, they lie parallel to each other. Okay, and because they lie parallel to each other, okay, they, you see, is a cellulose molecule line parallel to another cellulose molecule line parallel. So they are connected by hydrogen bonds. So the hydrogen bonds joining cellulose molecule is why we have cellulose microfibril. Okay, and cellulose microfibril joined by a lot of hydrogen bonds gives us cellulose fiber. Now this hydrogen bond is what gives cellulose high tensile strength. All right, and that's why it's able to provide support. So this needs hydrogen bond. Glycogen doesn't have hydrogen bond at all. It has only glycosidic bond. So hydrogen bond is not needed for its properties. Okay, but let's check. Hemoglobin is a protein. Hemoglobin needs hydrogen bond to form the secondary structure, the tertiary structure, and the quaternary structure. The folding of hemoglobin that gives it its precise shape, right, which is tertiary structure, requires hydrogen bond for that to happen. Water molecules, of course, they need hydrogen bonds. All right, so water molecules join together, they stick together because they form hydrogen bond cohesion. Yes, you got it. Cohesion is needed for water columns to be formed in xylem in order for water to be transported. You got it. So guys, this needs hydrogen. Glycogen doesn't even have hydrogen bonds. Hemoglobin needs hydrogen for each shape. This needs hydrogen to stick to another water molecule. So the one that doesn't need hydrogen bond is this, and that's the answer, glycogen. Okay guys, now this is supposed to be number 10, but don't worry, it's a typo error. What occurs during protein denaturation by extreme temperature, extreme pH? Okay, let's look at the things that occur. So figure it out. What do you think is the answer? I think this is our last question. So extreme temperature, please don't forget extreme pH, not temperature, extreme pH breaks two bonds. Ionic bond and hydrogen bond. It does not break. See, this one says, number one says, look at number one. Number one, read it with me. Let's read it together. Breakage of peptide bond leading to loss of shape of active site. Number one is a peptide bond is not broken by pH. It's broken by enzyme peptidase. So this cannot be there. Okay. Is not part of the reason, okay, why enzyme denature. But look at number two, destruction of existing ionic bond. Now, ionic bonds are broken by pH. An ionic bond helps to form tertiary structure, which gives enzyme their precise shape. If ionic bonds are broken, the tertiary structure will be lost. That means active site will be distorted and less complementary, and substances won't be able to bind to it. So 2 should be there. 3 says loss of alpha helical regular arrangement. Alpha helix is a type of secondary structure. Secondary structure, guys, is formed and maintained by hydrogen bond, and hydrogen bond is broken by extreme temperature. So once there's extreme temperature, hydrogen bond will be broken, this will be lost. Yes, that's correct. Now look at loss of protein tertiary structure resulting in loss of function. Yes, this tertiary structure, which is a precise 3D shape, is formed by 4 bonds: ionic bonds, hydrogen bond, disulfide bond, and hydrophobic interaction. So out of the 4 bonds, ionic bonds and hydrogen bonds are part of it, and both of them are broken by extremes of pH. So once they are broken, it will affect the tertiary structure. So what I'm trying to say is that number one is not affected, but the rest are affected by extremes of temperature. Okay, so that's what occurs. So the answer is what? Yeah, course 2, 3, and 4. Thank you. So this is where we stop for this class. Please kindly leave your questions, comments, like our videos, like it, subscribe. We are gonna hit you with series 3. Very interesting, don't miss it. Okay, remember, this is your schedule. Thank you for watching. See you. Bye.